Okay, welcome to Biostatistics 1. Here we're going to study about correlation and regression. This is our Unit 14 lectures, again, correlation and regression. Our main objective is to go through a data, what is a data, what is a scatter plot. Normally we use a scatter plot to find the patterns in a data set. So scatter plot is more or less a graph, a plot, and we can find the patterns. And normally it's two attributes. Let's say we have X and Y values and we can plot their points and we find the patterns. And also we're going to study a correlation. Correlation will give us the strength of the relationship between the two variables. And regression is normally going to be used for prediction. So first we start with the data. Here we say in the data we have the quantitative response variable, Y. We talk about the data measurement again. Quantitative data means the data that we can perform arithmetic operation. Here we have a value Y or variable Y. The variable Y is not as dependent variable. So a dependent variable means based on some independent values, the value of independent variable would determine the dependent variable. So example, we have the values of X1, X2, X3, and Y. Or we talk about only two variables, let's say X and Y. So we can say X is a dependent variable because the value of X will determine the value of Y. So Y become a dependent variable. So here we use the term explanatory variable X, which is again a dependent variable. So we have some historical data set here. And this data set is about 11 countries and the consumption of cigarette per capita and also the number of lung cancer that they have. This data was generated in 1930. So in this case, the consumption of cigarettes per capita will be the independent variable. And then the dependent variable will be the lung cancer mortality, 100,000 each one per 100,000 population for one. So let's see how this data looks like. So this is our data set. Again, this data set was generated in 1930. We have some countries, the cigarette consumption, and then the lung cancer. And the country is a nominal data, so we are not going to use that in our scatter plot. So we are going to focus on the cigarette consumption and the number of lung cancers we have. So for example, here in USA, we have 1,300 and the number of lung cancer per 100,000 population is 20. Great Britain 1,146. Let's say Canada 500, and we have 25. So when we have a data set like this, it's very hard to find a pattern in the data. We don't know if the cigarette consumption also increases the lung cancer. So for example, the more cigarette a country consumes, the more lung cancer patients they're going to have. So because of that, we are going to use our scatter plot here. So a scatter plot of those illustration of the correlation between smoking and lung cancer. So since we know that cigarette consumption is our independent variable, always the independent variable will be the x-axis, the x. So cigarette per capita 1930. Then the dependent variable will be the y, the vertical y. So here we can see that, yes, there's a correlation here, or at least there's some pattern here that the more cigarettes we consume, the more cancer mortality we have, lung cancer. But we can see that we have one outline data here. This is a very high consumption, but the mortality of that country is very low compared to the rest. But still we have again a pattern because majority of the data is forming almost increasing order, straight line. So again, a scatter plot make it possible for us here to even see the pattern here without doing any calculation any analysis, just plotting the values, we can see that there's an increasing pattern here. The more cigarette we smoke, the country consume, the higher number of cancer we have. So we should inspect the scatter plot. We say first, can the relationship be described with a straight or some other type of line? The direction, the points tend upward or downward. So if it's downward, it means we have a decreasing order. If it's upward, it means increasing order. In our case here, we can see that it's a upward. So which means as the consumption increases, the lung cancer also increases. Also, the strength of association. Do points adhere closely to an imaginary trend line? So this, again, the strength of association. We may, again, go through all this. And also sometimes we may have outline, as we saw in our data set. We have one outline. So here we say, are there any striking deviation from the overall pattern? You can see that most of the data is increasing pattern, but one data was just out of the increasing line. So here, judging the correlation strength, we say the correlation strength refers to the degree to which the points had held to the trend line. Sometimes the eye is not good. It's not a good judge of strength. And the reason why, because of the scaling. Sometimes we may scale our graph and we may see it as increasing or decreasing, or even there's no relationship based on the scaling of the plot of the graph. So here we say the top plot appears to show a weaker correlation than the bottom plot. We will say the plot. The reason why, because of the perception of difference in antifact of axis scaling, the scaling. So this is it. Now, these two graphs are the same data, but we can see that the bottom one, there's more relationship. The top one, there's no much relationship. We can't say it's a straight way. Kind of look, but there's a lot out. Now, the data are the same, but the difference now is, we can see here, we're starting from 340 to 520 with 20 between. But here we start from 240 to 640 with only 40 between. So here, the between is 20, but we also start with higher 340 to 520. So because the difference is very small there, this didn't come to, I mean, from 440 to 420, we have 20 different. And here is bigger from 560 to 640 differences throughout. So kind of the values here became more close. So that's why they said the plot sometimes it may give us, but the best way is finding the relationship between two variables is to find the correlation coefficient or Pearson correlation coefficient, which is R value. Normally this R value will be from +1 to -1, and we may go through that in a second. So scatter plot of the same data with different axis scalings. So it is difficult to determine the correlation strength visually. So because of that, we have to use the correlation coefficient. So correlation coefficient R, we quantifies the linear relationship with a number between -1 to 1. When all points fall on a line with an upward slope, then we have 1. This means all the points is on the line. Now, when all the data points fall on a line with downward slope, we have -1. So when it's decreasing, it's negative value. When it's increasing, it's positive value, between -1 to +1. Now, when it's 0 or very close to 0, that means there's no inner relationship. So we have 3 possible when we are looking for the R value. Either we may, based on the R value, we may say we have an increasing order or relationship or decreasing relationship. Now, when it's very close to 0, then we say there's no relationship. So this is a very good example here. So we can see here, all the points fall on the straight line. So this is called the perfect positive correlation, increasing. So R is 100%, is 1. Now here also we have a perfect negative correlation. All the points fall in one line, but it's decreasing. So it's -1. Now here you can see we have a strong positive correlation, but all the points doesn't fall in one line. So this will reduce the value of 1. Here we say approximately 0.9. As the data get more spread out, we can see the R is reducing. This gives us 0.5. With decreasing, the points are almost together and they are decreasing, so it's -0.9. Since everything is not on straight line. If it's on straight line, we may get -1.0. Now with here, the data are spread, we'll see that R will be -0.5, getting close to 0. So how do we calculate R? That's the formula given to us here. So the main thing we have to know, again, correlation coefficient is finding the relationship between 2 points, 2 variables, X and Y. So here we have the X values and Y values. So to find the correlation coefficient, first we should know the sample size. So it's 1 over the sample size minus 1. Then the sum of the z-score of X times the z-score of Y. And to find the z-score, we normally find the xi minus the mean divided by the standard deviation of the X value. Same thing, the each Y value minus the mean over the standard deviation of Y. So here we can see that meaning finding the z-score, if I have 10 values, then I'm going to find 10 z-score values and add all together. That will be my total z-score for the whole X. Y, that's why we have a lowercase I. So I can start, if it's 10 values, then I start from 1 to 10. If it's 20 values, then 1 to 20. So I have to find 20 z-score for each value. You find the mean of the Y values, then subtract the mean from each value, divide by the standard deviation of the values. So you do that for all the 20 values if you have 20. So here we say the correlation coefficient tracks the degree to which S and Y go together. Recall that z-scores quantify the amount a value lies above or below its mean in standard deviation unit. When z-scores for X and Y track in the same direction, their products are positive and R is positive and vice versa. So this is the circulation again of the R values. So we have our data set. Again, our data set, remember we have 11 countries. So the sample size N is 11. Then we have our S value for each country. And the S is our cigarette consumption per capita. So if I know the S values, the first thing I'm going to find is the S mean. So we have the S mean here. The total S value here is 6640. We find the S mean 6640 over 11. The same thing, we go to the Y. This is the Y value. We add all together, we divide by 11, then we get the mean for Y. Then you can see, as we said, we find the Z for each value. So the first value, 1300 minus the mean divided by the standard deviation. So these are the standard deviations. To find the standard deviation again, we have the mean already. Subtract the mean from each value, square it, add all together, divide by the sample size, find the square root of it. Actually, this is sample, so divide by sample size minus 1. Again, we did this in how to find the standard deviation variance range in Unit 4 lectures. So we find the z-score for each value. After we finish, we add all together. We find z-score for the Y each value. Again, the z-score means the value Y minus the Y mean, which is 20.54 something, then divided by the standard deviation of Y, which is 11.725. And we repeat that for all the values. So when we finish, then we can plug in the values. So to find R is 1 over N minus R, the sum of ZS and ZY. So I have 1 over 11 minus 1. Now the ZX, we have to come here. Where did we find it? The ZS is right here. So the ZS minus ZY, the total, we have to add all So the total was 7.374. It's good to do this in a table because you don't want to write 11 times, let's say negative 0.086 plus 2.848, and you keep writing. So in the table here, you can see that when we get the ZS for each value here, we sum it. We have Y, we find the ZY for each value, we sum it. Then we are looking for, the formula is ZX times ZY. So we multiply ZX and ZY, and we get the ZX and ZY. So we get 11 ZS times ZY. Then we add all together. So when we add together, we get 7.374. Now, when we get 7.374, that will be our sum of ZX, ZY. We plug it here, and we have 1 minus 11 minus 1. So when we do our calculation finish, we get 0.737. So we can see that our R will determine that we have an increasing order relationship between X and Y, but because of the outline, we can see that it's 0.7, not too strong. Mostly too strong will be 1 or 0.9 something, and normally will be 0.8 something or 0.8. So this is an increasing relationship. This is the best way to find the relationship between two values. Again, as we saw in the scatter plot, based on the scaling, sometimes it may be difficult to actually know whether the relationship is strongly increasing or strongly decreasing or no relationship. The best way, again, is to find the correlation coefficient, which we just did right now. So in practice, we're going to rely on computers and calculators to calculate R. You can see that this is only 11 values, but it's a long process because we have to find a Z for each value, and again, then multiply all. So imagine if our values data set is 50, 100, we can to take time to finish. So the best way to do this, we can either use SPSS, or we can use the Excel program also works. So here we say we encourage students to use these tools whenever possible. Any computer application, you can also use calculators, some graphic calculators, scientific calculators. So the SPSS, this is our output. We can see the cigarette consumption. We have the sample size 11. The lung cancer also is 11. Per capita, we have 1 and 0.737. This will be our R value, which we find here. PSA correlation, 0.737. And for lung cancer, the PSA correlation should be the same point. We are using the same sample size. So to use the SPSS, we click on Analyze, Correlate, Bivariant. Then we follow the steps from there. So the interpretation of R is very straightforward. That's the correlation. As we said earlier, if it's a positive value, then we say it's increasing. Negative value means decreasing relationship. If it's 0 or close to 0, then there's no any relationship. Or here we use the term association. So the strength, the closer the R is to 1 or -1, is the stronger the relationship association. +1 means increasing association. -1 means decreasing association. Now, the coefficient of determination is another special concept that we find. For example, when we get the R value, we can find the coefficient of determination, which is the square of the correlation coefficient. So the square of the correlation coefficient is called coefficient of determinations. And these statistics will quantify the proportion of variance in Y mathematically explained by X. So for example, if R is 0.737 and we find the R square, which is the coefficient of determination, we square 0.737, we get 0.54. Then we can say that 54% of the variance in Y is explained by X. It's explained by X. And also we have a reversible relationship. Here we say with correlation, it does not matter whether the variable X or Y is specified as explanatory variable when we are doing correlate. But with the regression is very important, which we'll cover later. So what we're trying to say is that if S is my independent variable and Y is my dependent, I get my R value. Now, if I change it and I say Y is my independent and R is my dependent, it doesn't matter. You get the same answer. So here we say with correlation, it does not matter whether variable S or Y specifies independent or dependent variable. Outlines is very important. Outlines can have a profound effect on the R. Actually, the reason why we get 0.737 because we have outline. If there was no outline, all the data are very close. We should have get closer to 1 or maybe 0.9 or 0.8 something. So the outline can have effect on the R value. So here we say the calculated correlation for this data set R is 0.82, but the single inferential observation in the upper right quadrant account for this large R. So if we have only this, we can see that it's like a constant relationship. But because of this one alone, it changes to increasing order. But this is not an increasing relationship, it's a constant. Also, we may have a non-linear. In this chapter, we have studied a linear relationship, but sometimes we may have non-linear relationship. This looks like a polynomial or something. So correlation apply only to linear relationship. This figure shows a strong non-linear relationship, R equal to 0.00. And correlation coefficient normally again apply to linear relationships. And here we say correlation does not necessarily mean causation. This is something we study in again statistics and epidemiology, causes, etc. For example, we can say that environment E causes disease O. I said the term cause, which means if the environment, if I'm in that very environment, the specific disease will come. But sometimes we may have in a correlation coefficient, we are not trying to find the causation. There may be let's say we have two variables. There's a relationship between X and Y or association, but there's no causation. A very simple example, we can say, okay, in the summer, let's say in summer in Florida, the sales of ice cream goes high. Sales of ice cream increase. And also shark attack also goes high. Summertime, there's more shark attacks. We can see that there's an association between shark attack and the sale of ice cream. But we cannot say that the shark attack causes us to buy ice cream, no. So there's association, but there's no, and this is what we come to the word locking variables or the confounding variable. So we may have another variable that may be the cause. In this case, it will be the weather. The weather causes us to buy more ice cream. And also the weather also causes sharks too warm. Sharks come closer to where people swim because maybe the water is too warm, etc. So a near perfect negative correlation was seen between cholera mortality and elevation above the sea level during 19th century. So we can see here we are looking for a correlation, but we now know that cholera is transmitted by water. So there's association or correlation between having a cholera and living in a high elevation above sea level. But there's association there because most people living in an elevation above sea level, they have cholera mortality. Those who don't live in that below or live below don't have it. So we can see there's a correlation or association. But there's no causation. The causation is water supply. Because the people living in the elevation above sea level were having different water supply than people living below. And the water was contaminated, and that caused the cholera. So this is again the diagram for the cholera mortality and elevation above sea level. So we have the cholera mortality and the mean elevation of neighborhood. So we move next to hypothesis testing. Again, we cover hypothesis testing topic already. As we said earlier, to test a hypothesis, first we may have a claim. So we may take a sample to test the claim, whether we should accept or reject. So it depends on what we are going to test. Here we are doing, again, correlation. So we are going to test the correlation value. So here we say the random selection from random scatter can result in an apparent correlation. So we conduct hypothesis testing to guide against identify too many random correlations. So I have a data set here and I want to take a sample. Look, the perfect sample we have. If I took this perfect sample, I'll say, yeah, there's a relationship between the S and Y. Now, if I take a different sample, let's say the one here, the one here, the one here, these three here, I can see there's no a good relationship. So because of that, when we take our sample, we can test it and see. So the process again, first, we state our hypothesis, the HO and HA. Here we say that our claim is that the correlation or population the row here represent population coefficient. R represent again the sample correlation. So we said equal to 0. If it's equal to 0, we know that it means there's no relationship. So our null hypothesis said there's no relationship. Now, or we can say that HA not equal to 0, which is two-sided. Or we can say greater than 0, which is right-sided. Or we can say less than 0, which is left-sided. So when we know the HO and the HA, we can do our test statistics. Here again, we are going to use a different formula, but you can see that the steps for hypothesis testing is the same as what we did in the previous chapter. We have hypothesis, state your HO and HA, test statistics. It can be whether you're using a z-score or using a t. Here we are using t-stat. We also can use the t-stat to test a small sample that the formula is different. So here we can see that, again, we are doing correlation here and we are testing for the correlation coefficient of population. So the t-stat will be R over SE. Remember, SE is our standard error. Here, the standard error is not the population. In normal distribution, we say is the population standard deviation over square root of the sample size. Here is different. The standard error is a square root of 1 minus R squared, which is the sample correlation coefficient, divided by N minus 2. N minus 2 also is the degree of freedom. Now, to use the T table, we need to find the degree of freedom. That will take us to the row. Then after that, we know the degree of freedom, we know the t-stat, so we can go to the T table and find the p-value. So we find the p-value, either using a software or a table. It's called a T table. And so first, hypothesis testing, then test statistics, then use the table or software to find the p-value. Then after that, we know the level of significance will be given to us. Then we use it to compare the level of significance. Now we make our decision whether we accept HO or reject HO. So let's see an example here. Here we have an example. Actually, we are using the same example of the 11 countries with their cigarette consumption and also the number of lung cancer they have. So here we know, again, we have 0. That means there's no relationship. No, maybe there's a relationship between two sides. So our HO say the population correlation coefficient, no relationship is equal to 0. HA will go against it, so it's not equal to 0. So first we find the standard error, which will be 1 minus R squared. We find this R in our previous example. Again, we are using the same first example for the 11 countries of cigarette consumption, the number of lung cancer. So we know R already. Then the N is 11 minus 2. So that gives us 0.2253. Then we find the square, the t-stat. This is just the standard error. Then the t-stat, again, will be what? The R over the standard error. So the R is again 0.737 over the standard error, which is 0.2253. So we get 3.27. Then we are going to the table. So we need the degree of freedom, which is 11 minus 2. So that gives us 9. Now, P should be less than or equal to 0.01 or greater than 0.005 by table C. So when we use a computer, the book said, okay, they use a computer, so they get 0.0097 by computer. But again, you can use the table, that's the T table. And this is our P range, should be greater than 0.005 and less than 0.01. We get 0.0097. So if we get 0.0097, let's say it's roughly 0.01. So we said that we had evidence against HO is highly significant since it falls within the P range. If P value is greater than alpha, let's say, then we're going to again retain the HO. But here we have evidence against HO means we reject HO because the P value is very small. So next also we talk about confidence interval. In correlation coefficient also we can talk about confidence. When we are doing hypothesis tests or inferential statistics, we may have some plus or minus values, some interval. So LCL stands for the lower confidence level, upper confidence level, and these are the formulas we use. And then the W with the bar, the formula will be square root of, again, here we're using the T. So T squared degree of freedom 1 minus alpha over 2. Remember, if alpha is 0.05, we get, I think, 0.975 here, which gives us, if it's a Z, like it will give us 1.97. But when we get the value 0.975, depending on the degree of freedom, we go to the degree of freedom and we go and look for this value, and that will give us the value we are looking for. So the same thing apply here. We look for the value in the T table because we know the degree of freedom and we know the alpha value, so we can find the value here. So the formula is we find this, then we add it to degree of freedom, DF. So let's see the example here. So I want to find the confidence interval for the population correlation coefficient. So we have established the following statistics for illustrative example. We already have the R to be 0.737. We know the N is 11. We know the degree of freedom is 9. So if that is the case, we know 95% confidence interval for population correlation is based on this information. So we use the following. 95%, we use the T. Degree of freedom is 9. The reason why, because N is 11 minus 2. So that gives us 9. 95% confidence interval. So we have 1 minus 0.005 over 2, and that will give us 0.975. So if I have T 9 and 0.975, I'll go to the T table, go to the degree of the row 9, degree of freedom, and then go up. And then this, I think we're doing one way. So we look for the value for corresponding to 0.975 on the degree of freedom 9. And that will give us 2.262. So if that is the case, then T squared will be what? 2.262 square, where the formula is square. So now we have the square over square plus the degree of freedom that gives us this. So now if I know the W bar from the formula, we can know both the lower and upper confidence level. So R minus W over R over 1 minus R times W. We get 0.243. The upper confidence level will be R plus W over 1 plus R times W. And that gives me 0.927. So here we can say this allows us to say that 95% confidence that the population correlation per capita cigarette consumption and lung cancer mortality is between 0.243 to 0.927. We know the association there are. So conditions for inference, again, we need the independent observations. We also need a bivariant normality, which R can still be used descriptively when data are not bivariant normal. So this will take us to our last session, which is regression. Normally, regression is used for prediction. So in order to do our regression, here we are doing linear regression, linear. We need to generate the model for the regression. So here we have a relationship between Y and X. We want to know if we know the value of X, we can predict Y. So this is how our previous data look like. So my regression is that I'm looking, this again, as I said, we said that this is linear regression. So we are looking for the best fit line. The best fit line is a line with the less errors. So if this is my best fit line, then I can extend it straight. And also, okay, if I have 1,700, the consumption will be 48. So how do we generate this line? Again, when you are using a software like Excel or SPSS, it's very straightforward. You have your data, then you select a regression equation after you do the process. But if we are doing it manually, then this will take us to something like a college algebra straight line. So the regression line equation will be y caret is our prediction equal to A plus B. So A will be our y-intercept, B will be our slope. So where the y predict value of y, so y caret is the predicted value of y. A again is our intercept of the line, and B is the slope. So in order to get this equation for prediction, we need to find the value of B. So B is R, standard deviation of the Y values over standard deviation of the X values. Here we are using samples, so XY, SX. Then the intercept will be A equal to the average value of Y minus the B times X average also. So if I know the A and B, then I can come with the equation. So that would be the equation Y predict, which is the Y caret is A plus B X. And we can see the slope of the line and the unit. So regression coefficient, here we say for the illustration data, we have established S bar, which is 603.64. So we know the Y bar will be 20.55. Then that's our average. So if I know the average of the Y, and I know the standard deviation of X, standard deviation of Y and R, then we can find the B. So the B is R, SY divided by SX, and that gives us 0.737 times 11.725 divided by 378.451. So that's our B. Then to find and the B is our slope. Now to find the intercept, we use A equal to Y bar minus B S bar. So Y bar is the average Y, then S bar is the average X or the mean X. So we get 20.55 minus the B value, we find it already, and the X bar is 603.64, and that gives us 6.77. So our regression model is 6.77 plus 0.022x. Now this is a very strong regression model. Now, any value of X I put here, I can predict Y. So if this is for years, let's say 2030, I put 2030 here, the answer I will get for Y current will be my prediction. And also we can use SPSS for it, which we can see the value. Again, this is our intercept, and this is our slope. So this will lead us to inference. So we say, for example, when we do our prediction, always we may get some error. So the actual population regression model, it will be alpha plus BXI plus E. So this EI is our error. So we say let alpha represent the population intercept, then B represent population slope again. So this is the formula we know we saw previously. And I will represent the residual error for the point I. So we may have error, so that may have effect on our outcome. Now, to estimate the standard error of a regression, the formula will be 1 over n minus 2, and the sum of all the residuals. When we say the sum of all residuals means all the x values, the predicted value and the actual value, the difference of the two is a residual. So when we find the difference of the actual S and the actual Y and predicted Y, if we add all, we get 0. So we square it first before we add. So when we come to the confidence interval here, we say 1 minus alpha 100% for population slope. And also the slope plus or minus t n minus 2, 1 minus alpha times SC, where SC is again different formula now. This is for our inferential stat. So we are looking for confidence level for our slope. So we have to establish the smoking and lung cancer illustrative example. We know N is the number of countries is 11. We know the slope value. We know the SY given 8.340. Then we know SX is given. Now let's calculate the 95 confidence for the slope parameter. So that will be 8340 over 11 minus 1 times SX is 378.451. So that gives us 0.006969. So here we say for 95% confidence, Tn minus 1 and 1 minus alpha over T equal to 9 and 0.975. That will give me 2.262. The 95% confidence interval for beta is B plus or minus Tn minus 1, 1 minus alpha over 2 times SCB. And that will give us our value C also. We also can do the t-test for the slope coefficient. The same steps. So first we state our hypothesis. This time we are testing the slope because in regression, the slope will determine the steepness of the line. So we need to, so now if we say the slope equal to 0, it means there is no any relation, because if slope equal to 0, remember in the equation, the slope will multiply the x, the independent variable. So we don't have any model to again predict. So we claim is equal to 0 or not equal to 0. Then we do our test statistics. We use the t distribution. By this time, the formula is B over SE. And SE is a little bit different formula again. So x, y given x over square root of n minus 1 times s. Degree of freedom is n minus 2. So whatever answer we get from the table, we convert the t-test to p-value. Then we test it with our series. So here we have the 0 not equal to 0. Remember the t-stat, b over SE. We know the b value already, the slope, and we know the standard error from the previous. Actually, it's written here again. So this is the standard error. We plug in, we get the t-stat. Degree of freedom is 9. So with 3.28 and 9, we can find the p-value. Here we say the p-value is 0.0096 using the t-table or any software. And because, again, the p-value is very small, 0.01, we provide a good evidence against HO. HO said the slope is 0. Here we see the slope is not 0, so we may get a model. So condition for inference, here we are dealing with linearity, with regression, linear regression. So we make sure our data is linearity. Also, we have to have the independent observations, the variables, then the normality at each level of the X, and also equal variance at each level of X also. And to assess the conditions, we say the scatter plot should be, again, visually inspected for linearity, normality, or equal variance. Plotting the residuals from the model can be helpful because residuals, in this case, we will see the predicted Y values and then the actual Y values. The difference of each one based on S value, we will see everything. So this is residuals in smoking and lung cancer. So we have our data set again. X is given, Y is given. This is the prediction values. So if this is the prediction value, we know the actual value of the Y. So we find the actual value of Y is 20 here. Based on the regression, the predicted value was 36.4. So we have a residual of negative 16.4. Residual will always be the actual Y value minus the predicted value. So we can plot both the actual Y and predicted Y, and we may see. So residual plot for the illustrative data set is given here. With late experience, you can get a good at reading residual plots. So an example of linearity with equal variance or linearity with unequal variance, or example of non-linearity with equal variance also. So this will be the conclusion of our correlation and regression lectures. So in these lectures, we cover what is correlations. We start with what is data, how we can use the scatter plot to visualize our data. And we mentioned that that's not the best way to find association between two variables because of scaling. So we learn how to find the correlation coefficient, which is a perfect tool to find the relationship between two variables. And we said we have the R values, the correlation coefficient is lowercase r, to be from -1 to +1. If it's -1, that's very strong decreasing relationship. If it's +1, that's very strong increasing relationship. Now, close to 0 or 0 means there's no relationship. Then from there, we move to the concept of, again, regression, how we can predict, and the regression equation. And we also talk about hypothesis testing for both correlation. If I'm doing hypothesis testing for correlation, I will test the population correlation. And we have the formula for the test that it is. We have to use the t-table to do that. Then it's the same thing in regression also, we can test the slope. Since the slope determines the linearity of the equation, we can also test the slope for hypothesis testing. So again, wish everybody the best in this class and look forward to seeing my next lectures. Thank you.